Okay, we're going to go through this. It won't take too long. I promise it will not take too long. So, all right. So, okay, so this is number one. Everybody see that? Okay. So the De Morgan that you should be able to do De Morgan in your sleep from all the times that we've done it. A naught and D, and that is ORed with F, and then C, and not E, ORed with the knot of B. And this would be the knot of G. All right, so that's your question. You can have the F on the other side. It doesn't really matter, but that's one way of doing it. Okay, number two, the right answer is 1000, 1101, 0100, 1000. So this is one of those times when you add you subtract a negative number from a positive number and get a negative number, and this is a negative number. That's a negative number, but that's okay. Number three, there's two good ways of doing this problem. Either way works. One is with a counter, and the other way is with one-shots. Either way is acceptable. Now, if you use a counter, counters use a one-shot, and basically it's a count to three, so the S1 is all you need, and then it counts up to 3. Count up, let's call this counter 1. And then if you're doing Siemens, you have an accumulated value over here, call it accumulated value. And if you're Allen Bradley, you just counter 1.ACC. And then you also have a preset over here of 3 if you're Siemens. If Allen Bradley, it's counter 1.pre is equal to 3, and you can do it that way. Now, how do you reset a counter? Well, when it gets done, counter 1 dot done, that's Allen Bradley, or dot Q for Siemens, you reset it. Somehow you reset it. With Allen Bradley, you do a RES, and then with counter 1 is your title. Or if it's Siemens, you have a reset right here on the left-hand side. Okay? So that's one way of doing it. Now, how do you get your H1 and your H2? H1 is greater than or equal to 1, or greater than equal to 1, okay? Okay, so it's count equal to 1, greater than equal to 1, and that would give you H1, and greater than or equal to 2 would give you H2. Now, the other approach is a little bit more dicey, but it works, but it's not as easy as you might have expected. With this approach, you have to get the information. If you do the one shot off of S1, okay, call this A. Now, A is a one shot on the leading edge of that. Now, the one shot has to be A and not H1. Gives me one called H1, okay? Now, but notice, you have to do this in order. Let's just call this X1. And then A and H1 would give me X2. Now you can use those seal circuits, but you can't use them up here because if you set H1 here, then this affects this. Do you see that? You have to set these bits before you can do your seal circuits. Okay? And then A and H1, A1, okay, but not, okay, so that sets that, and not H2, excuse me, not H2. And then A and H1 and H2 give me X3. Now you can set your seal circuits down here. You can do that all day long down here, but you can't do it until you've got these bits set. This is tricky. This is scan-dependent logic, and that's where you fell into a trap, most of you, and that's why I took off 3 points. I didn't take off a lot, but I took off 3 points. Okay, I think I took off 3 points. All right, does that make sense? You cannot, most of you, that if you put a counter down there, you got full credit. I did not take off hardly anything if you recognize that a counter would do the job. I thought, at least you saw that a counter will do this job, and a counter will, leading edge, do this job. Now, you didn't handle the reset right, maybe, but you would have gotten it probably pretty quick. But recognizing that that possibly could have been a counter, great insight. Okay? The other side of the coin is, if you did it this way, the scan-dependent nature of this code makes it so that this affects this, and if you go down your code, you set your H1 before you look at it here at your H2. Doesn't work. You got to set some intermediate variables and then set your H1 and your H2. Okay? So it's picky, but it's real world. And this is not one that I invented. This is one of the Germans' problems that they did. I apologize for sometimes for using their stuff, but on the other hand, that's okay. It's what it is. Okay, number 4. All you have to do here is just this number 3 part. So again, I don't want to belabor this, but that's all you have to do is the number 3 part. So heating occurs when the heating element, okay, so basically you have to say I am in the phase that is the heating phase, or the heating occurs when the heating element stays on. Okay, so, and this is in the evaporative phase. So you just say, I'm doing evaporation. So that's what you got to do, evaporating. And I have, turns on when the temperature reaches 80. So greater than equal to 80. Oh, it's a temperature switch. So that's not it is not a greater than, it is a switch. So this is a, this is a greater than switch. So this would be, you're in the evap, and you're greater than 80. And that turns on the temperature, okay? It turns on your heater. This is backwards, but it reads this way, so that's what you do. And then also, as long as you got your evap going on, you're doing your agitator. So that's all that is. Not a big deal, but just reading through that was all it was. Okay, now this next one is a little bit more dicey. Number 5 is a little bit more hard, but it's still very doable, all right? So this one is one where you have a run cycle. So you're running as long as blah, 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 whatever. You don't know what that is, but you're running as long as something's going on. So when you hit the run button, you're dumping material. So this is called your push button, Ted. It's a push button. So this is a push button. It's your start push button. Okay? And you seal that circuit, and then you you have a couple of things that can stop it. This is run. And you seal it. You're running, okay? Now, on the leading edge of the run button, you move the weight to a place called initial weight. Okay? So you grab the weight at that point in time, and then you move it to a place called initial weight. Now, when you're in the run mode and there's something else going on here, you're not halted. We're going to define halt in a minute. And you also want to find the weight of subtract initial weight minus 500 target weight. So you get the target weight, and then you say, as long as I am running and I'm not halted, and I am greater than my target weight, I'm going to vibrate. Okay? Now the halt button is, and then when it's less than or equal target weight, my present weight, or the weight now is greater than or equal to the target weight. We keep running. It's less than or equal, the present weight is less than or equal to the target weight. Stop. Okay. And the other thing would be a stop button. And the other thing you can do is the halt. When you're in the run mode and you hit halt and you are not reset, not resume, you are halted. Something like that. Does that make sense? I gave full credit, partial credit for a lot of something. I call it the 20-minute rule. I basically, if you get close, but you don't quite get something like this, but you get somewhere close, if you can within 20 minutes probably get it working or close to working, I'll give you credit for it. If you got most of the elements in there, anyway. Does that make sense? What's this course about? Right here. Being able to write code that starts and stops processes and gets you started down the path to being able to, in a real factory environment, to be able to write code and be able to make it run. And whether or not you get that all in this course or not is up to you. Some of you get very good at it. You like it. You do it a lot. Some of you hate this with a passion. You come back to me at some point in time or you drop out or whatever. I'm not saying anybody should drop out. I'm just saying people to say, I got it. I don't like it. I'll never do this the rest of my life. That's okay. At least you know. Some people like doing this kind of stuff. Some people don't. Some people gravitate toward it. Some people don't. That's what this course is about. It's trying to get you to somehow feel good about this, or this is something that does not give you any feeling at all about anything good. It's up to you. This is anyway. Number 6. This one is turning something into, like a set reset circuit. So again, what you should have over here is a set and a reset. And then this should be for the bit called F. So the thing that should turn it on is A and not C. And the thing that should turn it off is the negative of these things, so not equal. Not equal to 250, and then the not of D and the open of E. Or together, give me my reset. Something like that. And number 7, probably the easiest one on the test. We went over this 2 or 3 times, I think. This is EN is .IN for Siemens. .done is .Q. And they don't have a timer timing bit, so you have to say .IN, but not .Q would be my timer timing bit. So timer1.in, timer1.q, timer1.in, but not timer1.q. All right. And number 8, same thing. So here, instead of compute, it's a calc block. And instead of these values, the values come in from outside, and there's 4 of them. And they val 1, val 2, val 3, and val 4. And these are N1, N2, N3, and N4. And you have your equation up here, N1 times N2 plus N3 times N4. And you have an output that is the word total. And you're done. I wanted you to get the idea that they do the same thing. They don't look the same, but they do the exact same thing. And this is how you write arithmetic equations. This is how you write equations in a PLC, exactly this way or this way. Get used to it. This is how it's done. It's kind of crude, but it works. If you're in ladder, now if you're in a sequential program or a procedural language, you write it just like you would in C or another procedural language. This one here is straight out of the book. We did this one in class. Okay, so how do you do this one? All right, so here, you have competing resources, so you have to block one while you're doing the other one. So you have 2 basic seal circuits. One that does, and this can be out here. It doesn't have to be in here, but you have to have it one place or the other. So you have to say fill bin 1. Okay, so this has to be for fill bin 1. And this would be not a fill bin 2. And then you have to have one like this for filling bin 2. So this seals on as long as you're filling bin 1 until you're satisfied. This does the same for bin 2. And it locks it up, and it won't allow something to go the other way. Okay? From this point on, it's fairly straightforward. You run your conveyor. If you want to run your conveyor to the left, conveyor left is, okay, so fill bin 1 goes conveyor to left. Fill bin 2 is conveyor to right. And then either one runs your screw conveyor. And then the upper one is just basically a simple fill circuit with a high and a low. Fill storage bin 1. Any questions about that? Competing resources, you have to block the other one so that you can only do one at a time, and then you seal it. If you have more than 2 resources, what do? You don't do it this way. Why not? Why, if you had 4 or 5 resources, why would you not do it this way? Because if 2 came open at the same time, you would always favor the one that was the first one programmed. Make sense? Okay, so you'd always favor the one that was first in your program. You can't choose them both at the same time. So how would you solve that problem? A FIFO stack. A FIFO stack. And you can do the FIFO stack either with Allen Bradley or with Siemens, but a FIFO stack gives you the ability to put it on a stack and then wait. It's a queuing problem. It becomes a queuing problem. This is a queuing problem, but it is really, really, really simple, and it's very straightforward. One blocks the other, so one will block the other. But if you have more than 2, if you have 3, 4, 5, 6, 7, 8, then it becomes a queuing problem, and you must go to a FIFO. You cannot use this technique if you go to more than 2. So again, not a big deal, but something. All right? This one probably is the most controversial for the simple reason that even though it's the same problem that I had before, but I added a twist to it, and the twist makes it even worse because now I'm asking you to, how do you want to say, take a weird problem and make it even weirder. And after I did it and I thought about it for a while, I thought, it's not like I can just give you this one, but I was very generous with my partial credit on this one. Because, why? Because I tell you that C2 is not in your programming. You're not programming C2. It's somebody else's program. Somebody else is running the show with C2. But you know what C2 is doing. You know when it's running. But you want to stop this conveyor after you've run the box off on this conveyor so far. And so use a timer for that. But I don't say why, and I don't really know why. Maybe there is a person that is writing the program for C2 that wants to know when you stop your conveyor and he'll stop his conveyor. I don't know. I don't have to know. The rules of this is kind of weird, and if it bothers you, that's good, because this is not really good logic, but it's what it is. So basically what you have to do is you have to do the basic problem, which is seal the circuit. When it says run, you say, okay, I'm going to run. But the run is not the one that runs the conveyor. The run is the one that says, get the box to, this says, please get the box to conveyor 2. So this just says run conveyor 1, please. Okay, it's a run please button. Okay, and this is, the push button isn't, this coil over here is. It says, so the push button is just the push button. The coil is the one that says, please run C1. That's this one. That's this seal circuit right here. Please run C1. Okay. When you get over to C2, when you run the box past the trailing edge of this photo eye, that drops this out. But now we added a timer to it. So what actually happens is the photo eye, the knot of the photo eye, starts a timer, and the done of that timer turns that off. Okay? That's all it is. Weird, but that's what it is. That's all it is. So if you had anything close to that, oh, and then please and C2 run C1. So that's that one. Enough. Anybody have any overriding questions? I know you probably have some point questions afterwards, and we'll have time for that. Okay, but that's how I would do number 10. And you probably have some varieties of that as well. So what's ahead of us? The heart of this course is what's still to come. And I basically call this the big box portion of the course. The big things that you can do with the PLC and with the logic that we've learned up till now. But basically, you use that in conjunction with something else. Okay? Does that make sense? You use what we've built up till now, and we use that in conjunction with some other device to do some specific action. All right? And Wednesday night, I want to talk about matrices. Tonight, I want to go back and I want to talk just a little bit about the points that we've got and the areas that you can get points in a hurry in. I do want to state very adamantly that this course isn't working unless I go home every night with my folder about an inch thick with, there's 60 people in this course. Okay? My folder, and I hate this, believe me, I'm grading these myself, and I hate this, but on the other hand, my folder ought to be about an inch thick every night I go home with labs, okay? And I look at them, and I just note that it ain't there. So again, I'm giving you more points toward the end for things. That being said, the points are the points, and you know, it's your course. You got this course is styled to get you into the lab and get you sitting there in front of the screen trying to do something with a PLC. And as you do that, the more you do that, guess what? The better your scores in this stuff will go, and the better you'll learn. It's a strange course. Most of the time you sit and you study with a book and you're trying to get an equation to work. In this course, you're trying to get some circuit that has some meaning to something out there to work. And it's a different animal. This is real-time computer programming, and if anything can happen bad, it will. And this stuff will bite you again and again and again. So the more you work at it, the better you get. And if you like it, it's a career. If you don't like it, you can endure for the semester. I won't flunk you. I shouldn't say that, but you know, I guess I shouldn't say I won't flunk you. I am inclined not to flunk anybody. I'm inclined to give a lot of A's, B's, and C's. This is the first time that I've taught this course to this many people since 2023 in the spring. And I honestly, 2022 in the fall, I had 67 people in there, and it was crazy. And that's when I developed this spreadsheet of these points. But it can be done. Everybody can have a segment of time. You can go into the lab and get these labs done. A lot of people get A's, but it ain't guaranteed. So again, I don't want to scare anybody. I don't want to try to scare anybody, but I just want you to understand that the points are the points. Okay, I want to go back and I want to talk about the syllabus, Everybody understand the labs are 40%? Everybody understand that you have to have 20 points by the end of March, 1st of April. I have two grade sheets. I have the before April 1st grade sheet and the after April 1st grade sheet, okay? And yes, there's a little bit of give. There's a 3 or 4 day give. Oh, okay, I'll give you a couple of days. But once about April 5th starts to seal in, April 3rd, whatever, in that time frame, no more, done. So here are your points. And you start getting 4-pointers in chapter 8. That second lab in chapter 8 gives you 4 points. And from then on, it's that. Now the bike lab, I can move it downstairs, or I can get somebody to move it downstairs for me, but it's up in the back of 2380. It's a nice lab if you like exercising and that type of thing. And it has analog with it as well. If anybody wants to do the bike, let's just show a hand. Does anybody want to do the bike lab? 1. Anybody else? 2. Okay, so we'll get it downstairs. I'll get it so you can have access to it. I promise you we will have access to the bike lab. Okay, we'll get it going, and it'll be down in 1100, okay? Now, here's where they start getting good. The chapter 15 labs, there's 2 groups of chapter 15 labs. The 2-point labs, which are echoes of the labs that are in chapter 7. Now, chapter 7 is supposed to be without an HMI, and then chapter 15 is supposed to be with HMI, but I started it from the very beginning giving you the option of HMI. So if you did them in chapter 7, you can't do them in chapter 15 if you use the HMI. But if you didn't use the HMI, if you wired the lab in chapter, if you wired the one of those labs in chapter 7, and then you want to do it again in chapter 15, I'll give that one to you. That's not a lot of points, but it's a couple of points. The animation stuff that they have in chapter 15 is, those are new, and hopefully that's something. Now, you notice that there's 2 Allen Bradley and 1 Siemens sign-off for these labs. The second Allen Bradley is that factory talk, okay? And we don't have that up and running. We do have it in 2350. So if you want to get 6 points here, you can, but the third one is factory talk, okay? So only in 2350 can you do that. These points start the 8-point labs, and one of these is a report. These are not hard labs. You look at these labs, some of them are not hard labs. Some of them are, well, you can see them for yourself, see what you think. Chapter 16 is communication stuff, and these are all 8-point labs. I went from 4-point to 8-point labs here because I think this is important if you are working in a PLC environment in a factory or any place where they're talking about hooking PLCs together with other equipment. You're going to need to know some of this, and it's almost like you've got to know some of this stuff, but it's not heavily taught. I don't go into great detail, but peer-to-peer is one PLC to another PLC. If you can transfer data back and forth, and those you can knock out in an hour or 30 minutes. If you're really into it, you can knock that out in half an hour to an hour. That's an 8-point lab you can knock out in an hour. 1 8-point lab in an hour. That's not bad. But again, that's something that you might be interested in. Chapter 17 is on motion control, and to be blunt, the Siemens lab there is given. If you want to type it in verbatim, you can, and it will work. Okay, so the Siemens lab, if you want to highlight in chapter 17, the Siemens lab, it's at the very end of the chapter, but it's all typed in, it's entered in, because when I was teaching this at one point in time, I could not get the students to try the lab. So I gave them the lab, and I kept it. It's there, it works. You can have it. It's an 8-point lab, but it's a good lab because you're spinning, you're doing single axis motion control, which is something that, again, when we talk about this in the lecture, you probably will say, that's an interesting lab. Now, chapter 19, we're going to talk about that chapter a lot later, but right now, if you have an auto controls course and you want to understand how the auto controls course works, all you have to do here is to get a faceplate to work. These 2 labs you can download and get it started because these are labs that are taught in EET 4450. So I actually, in these 2 labs, there's In EET 4450, there's two labs, the ball and tube and the tank over tank. And there's a starter program for both of them. And all you have to do is to add a faceplate. And you're done. I purposefully did not put faceplates with either of those just for the fact that I wanted this class to be able to say, okay, I added something, I added a screen with a faceplate. And you say, what is a faceplate? Well, in chapter 19, I talk extensively about faceplates, and you don't have to make the worst, you don't have to make it the worst one in the world, but you need to have with bars going up and down, that type of thing. And that's the common explanation of a faceplate, okay? So you wonder, what is a faceplate? It's laid out in, as they say, in spades in that chapter. So all you have to do is add a faceplate. And it's not hard, okay? You cannot do those with Allen Bradley. You can only do those with Siemens. I apologize for that. We used to have labs with PID with Allen Bradley, and again, the equipment has died. Chapter 20 is, so you download in chapter 19, you download these. These are downloadable labs that then you just modify. That's all it is. Any question about that? Then number 20 is a wiring only lab. The safety lab is wiring only. But it's a bear. But if you follow the directions, you can get that to work. And it teaches you basically everything about the safety programming that you really, really need to know. It's a very good starter lab to get you into the safety issues. Okay, if you want to say that you don't know anything about programming a safety PLC right now, that's valid. But if you did that lab, you could not say that anymore, because you would understand the concepts of, there's a starter program that you download, and then you wire it. And if you wire it and you get it to work, you're in. There is a big hint in that lab, and that is the relays that they have on the lab setup itself are big, and they don't take size 18 or smaller gauge wire. So you basically are encouraged to use the relays that you use for lab 2. So please, if you do that lab, substitute, and it's in the hints for that lab are all listed, but please do not try to use the big relays that are on the rail. Please use the small relays that you did in lab 2. Substitute the relays, and it's in the book. It tells you to substitute the relays. It encourages you to substitute the relays. Please take that to heart. Any questions about number 20? Okay. Then the Cognix. Cognix is the eyes. It's not a PLC, it's a camera system. And we have 8 of one variety, and we have 3 of another variety. We have 8 7802s. We have 8 7802 variety, and we have 3 of the 3805 variety. These are supposed to be more AI than these. These do not have no AI in them. These are supposed to have some AI in them. But if you can go through and do the labs through 5.2, again, these labs are in the EET 4450 folder. You do lab 3, lab 4, and lab 5 to 5.2. Take a picture and you get 8 points. Takes you all about an hour and a half to 2 hours to do. All right, so I'm encouraging you to sit there and do some of these labs, and they will give you a lot of good information, and they will give you some heavy duty points. So I want you to do some of these labs. Some of you have asked me about the Rubik's Cube lab, and I say that's a negotiable. I will go up to almost all of the 40 points if you do it, a lot of it, but not if you don't. This is one of those times where it's a high risk, high reward, but if you just sit there and don't do anything or do very little, I don't give you very many points. If I realize that you basically stood me up and didn't do very much, I will consider that. This is one of those things where if you've done PLCs before, and this is your second time through this course, or you're doing something else, this is not your first rodeo with this course, I will consider that. But you cannot just blow it off and say, I can't, that's all I did and I failed. So that will knock your grade, and I can't give you an exact points total, but I won't give you 40 points if you don't do much with the Rubik's Cube. If you do a lot with the Rubik's Cube and go a long distance with it, I will give you a lot of points because it is worth a lot of points. It's not an easy program. It's a heavy lift. But if that's something you want to do and you're bored, you don't have any other things, no other game in town, your team is out of the March Madness and all that kind of stuff, and you want to do something, go for it. But you got to tell me, you need to let me know soon, because otherwise, if you just come in the last day and say, I did the Rubik's Cube and I didn't get it to work, guess what? Show me how far you got. It won't be worth much unless I can see a lot of work that has been done on it. If I see work, exponential work, I'll give you exponential credit for it. But I will not give it to you just on the fact that you say that you did some Rubik's Cube work, okay? And I also give you a negotiable one here that basically says, you come at me with another project that is viable, student initiated. If you want to do something, it's got to be with a PLC. It can't be with Arduino. It can't be with a embedded system. It's got to be with a PLC. But if it's Allen Bradley or Siemens, go for it. I'll listen to you. I'm not hard-nosed, but I do not give everything away because what I've got works. All right, now this Festo stuff up here, this right here is not the suitcase labs, okay? This Festo up here is not the Festo. I'll show you if you want to do the Festo labs. In the back of 2350 there is a machine, okay? It's a merry-go-round machine, and it's a state machine. It's like if you want to do state diagrams, and I'll give more than 2 points for these. If you want to do one of those, any one of those, I say any one. If you want to do one, I'll give you 4 instead of 2 points. I'll give you 4 points for it. Okay, but each of those can be turning around, and then they do exactly what I described with the thing that I talked about with the steel, the Nucor steel program. They're the exact same style of going around in a loop and then handing off to the next one, and then it hands off to the next one, hands off to the next one, hands off to the next one. I'll give you, for every one of those loops you do, I'll give you 4 points. That's not a bad way to go. But again, I wouldn't jump into that unless that's something that you really want to do and you want to see how state diagrams work. That's a state diagram program all the way along. But again, you have to decide if that's what you want to do. You may explore it a little bit, look at it. I'll help you if you want to get into that, but that's what that is. That's not the suitcase labs. Okay, now, I got about 10 minutes, and I want to go through chapter 12 in about 10 minutes. But I can, because it's not much. This is one of those, it's not a throwaway chapter, but it's not a chapter that has a lot of depth to it. Because it's just one of those chapters that you need, or I felt you need, but it's not a major, it's like a B League chapter, okay? It's not an A League chapter, it's a B League chapter. It's not one that you would want to write home and say, I got everything about chapter 12 that, okay, that, I really understand chapter 12, okay? So basically, this is a chapter that has to do with what? Well, this is a chapter that has to do with being able to look at historically programming issues that specialized instructions had to be invented for because we didn't have anything that would do. Does everybody understand that PLCs do some things very well and they do some things very poorly? And these are some of the things that they do very poorly. Okay, what are some of the examples of that? Well, FIFO, they don't do FIFO very well. So you had to come up with an instruction that dealt with FIFO, all right? And that instruction is down here, and it is an instruction that is in the Allen Bradley. It is not instruction that is in the Siemens, but again, like I said before, if you don't find the instruction, it doesn't mean they don't have it. It just means that it's not in the outward layer. It's that you have to go find it. It's in somebody's library someplace, but you can see it. It's just not outwardly available. But they've got them. Okay, they've got them. But these are some of the extra instructions that are in both of them, and I just bring these up because they're there. But here's the FIFO instructions. Now, this is a pictorial example of FIFO right here. Okay, so this would be a canning or a like down on Hill Avenue. There's a Pepsi plant, right? So every day they're going to make what? Pepsi, Diet Pepsi, Dr. Pepper. I don't know if they make Sprite down there or whatever, but they make a number of products, right? They make a number of different types of, and each one of these day tanks, these would be what you would call day tanks. Each of these tanks would go to a canning line. So you have a master mixing station with a master tank that you would mix the stuff up, and then they would go to one of these lines, okay? So maybe they have one mix tank, maybe they have two, I don't know, but typically they have one, and then they go to one of these lines at a time. So like I just talked about a little bit ago, as long as everybody's full, you're okay, but when one hits empty, what do? When one goes empty, you put it on the stack. And if it's not making anything, what do? You make that kind of pop, or make that kind of liquid, okay? So now you're making this, and when you're done, you fill that tank, and you're back in business with that guy full, okay? Well, in the meantime, two other ones went low, B and D. Who went low first? You have to decide. Tank D went low before tank B went low, right? In that case, what do you do next? B and D. What do? B goes into the mixed cycle, and then you plop D in still on your stack, and you move it up to the top of the stack. That's all it says. But it's a specialized instruction. Also in this section, we talk about tracking. And they have specialized ways of tracking product on a line. Now, I do not like this approach, but it's used a lot. Why? Because it's very visual. If you have a product going on a line, what you can do is you can put a pulse tack, and every time that the pulse pulses, you move the bits one bit to the right or one bit to the left. It's a shifting instruction. You're shifting. So basically what you have is you have these bits going down the line. You actually see them moving through the array. And this is used, believe it or not. Why is it used? It's very visual. Very, very visual. You can see them on the screen going down the words. Okay? Why would anybody do this? Because an electrician can actually see it. They can see that as the bits move down the words, you can see the product moving down the line. Okay? What's wrong with this approach? Well, these do not carry with them any information other than the fact that it's a product. It's not a product A or product B or product C or product D. So each of these, if you have 4 products, you have to have 4 shift registers. Not a good way to go. But if that's what you want, you can do it. People use this approach. There's a much better approach that I talk about here, and this one is down here. which now it gets you into the what? Another language. This is a procedural language. It's the procedural language from Siemens and Allen Bradley, SCL. And what does it do? It's if then else statements. It's go, it's for next statements. Okay? And if you do that, you can do tracking very efficiently. And it's a procedural way of doing tracking. You can track by part. This is how I did it at LOF, by part, and you can be very accurate, and you can also know the position and a pattern or a recipe or a identifier for each of those parts, so that one may go left, one may go right, one may go through. But using the procedural language is the best way to use for tracking, my opinion. So that's one way of working at that. Okay, now, so instead of state diagrams, if you track the part by a pulse tech, you can know exactly where the part is at all times. One of the ways of doing it. Another way of doing it is to have an identifier on the part, a barcode or an RFID tag, and then you, as the part goes by, you can read and say, now who are you, what are you, and you do accordingly. So all those are practical approaches to being able to track product down a line. But I want you to know that state diagrams are not the preferred way to go when you're tracking going down a line. Why? Because once you get off, you're off until something gets you going again, correct it. But state diagrams are not the best way of tracking product on a line. So that gets you through chapter 12. Very quickly, done, not a big deal. But at least you know a little bit more about tracking and some of these other weird, that's not a weird instruction. It's an instruction that you've got to be able to do, because you have to be able to write that, but it doesn't, it's not an instruction that you would be able to do easily in a program controller at all. So you have to have these specialized instructions. Okay, enough on that. I do not think of anything else. I'm going to dismiss you, and people have questions or concerns, I will be here for a few minutes and we can talk, okay? Take care.